All right, looks like I got the right screen showing. Thanks to everybody for joining us today in our latest webinar in our operator certification series. I think the background image here is a really good one for today's topic because it really kind of alludes to what we're going to be talking about today, which is flow rates and detention times. These are two interrelated concepts you're going to need to have a firm grasp on for both the operator certification test and in your day-to-day work. We're going to start by talking about where flow rates and detention times show up in wastewater treatment, which is just about everywhere, and why they're important from a theoretical standpoint. And then we'll move on to some volume and area review because that's really going to help with the problem solving. And then we'll move into flow rate and detention time problems. And along the way, we'll talk about conversion factors, some typical parameters you might run into as well. And I'm taking this approach because I find that if I can understand and visualize what's happening in a process, then solving a problem about that process becomes a lot easier because I can see sort of in my head what's going on. I've got a good frame of reference for evaluating test answers that might be given to me and checking my math and sometimes even discounting some test answers because they're just obviously wrong. Though of course you always want to actually do the math and not just discount things out of hand because sometimes you will get questions that have really bizarre answers. Speaking of test questions, if you've got one, grab a calculator, pencil, and some paper. We are going to be doing some sample questions along the way as we go. You can also, from the chat, download the NMED version of the formula sheet for conversion factors and formulas that you would use in a wastewater test. You can use this today. You can keep this copy for study. I find that it's a pretty concise and thorough set of formulas and conversion factors that you're likely to need for an OPCERT test. But of course, remember, this is a national broadcast across a wide variety of jurisdictions. This is NMED's sheet for NMED's test, for the New Mexico test. If you're in a different jurisdiction, although you're probably going to have the same formulas, they might not be laid out exactly the same way. So it's a good idea to check with your local certifying agency and get copies of whatever test materials they provide so that you can get familiar with them and comfortable with them so that when you're taking your test, you're not looking for in the wrong places for that information. So with that little preliminary bit, let's get on with the show and talk a little bit about flow rate and detention times. And start with a rhetorical question. Why are these concepts so important to wastewater treatment and actually drinking water treatment for that matter? Well, for one reason, they're used a lot. If you think about the topics that we've covered so far, the topics of later sessions that you may have seen advertised, you'll see how often these come up. And of course, in your day-to-day working life, if you're actually working as an operator right now, whether you're a trainee or you've been at it for a while, you will recognize that these are numbers that you have to have some facility with, things that you have to understand. For example, as we talked about in an earlier session on collection systems, collection systems are designed with certain flow ranges in mind, so that, for example, they can maintain their minimum scouring velocity during average or peak flows and don't get backed up. Like I said, almost everything in wastewater treatment is in some way or another flow dependent. Treatment plants, same thing. They're built with specific flow ranges in mind. Think about the information that you probably log for reporting, like average daily flows and peak flows that your facility handles. The design parameters for your facility determine how much volume your plant can treat in a given time to the required standard. If the flows are too high or too low, that can cause problems. So it's really good to be able to understand, what those design requirements are and how you can influence them by changing flows, which in turn impacts detention times. And on the detention time topic, every process in wastewater treatment or drinking water treatment takes some amount of time in order to be effective. Sometimes it's a short amount of time, sometimes it's a longer amount of time, but they do take time. Virtually nothing is instantaneous. And flow rates, the volumes moving through the plant, impact the time that those processes have to complete. Sewage is constantly flowing into your treatment plant and hopefully clean effluents flowing out after being passed through the various treatment stages that your sewage undergoes. One of the ways that you ensure that the processes are working properly is by modulating the flow of effluent through different basins in the plant and ensuring that the detention time, or the time that effluent spends in a specific part of your system, is adequate for the treatment process in question, whether that's primary sedimentation or secondary treatment or disinfection. All of those processes take time, which, as we'll see, where flow and rates and detention time really kind of come together and play a big critical role in sewage treatment. So, for example, your clarifiers, they use gravity and sometimes flocculation to separate solids from liquids. It takes a certain amount of time. The average time that the water is staying in your basin is the detention time. We dial that in by controlling the speed with which effluent enters and exits the clarifier. And yes, there are actually fish in that picture. A little later this year, we're going to be doing a podcast or video on this particular treatment plant and how they incorporate koi into their treatment process. But that's a very interesting story for another day. But I mentioned trying to visualize what's going on in processes, and I think as you're learning your trade and learning the job, it's a good idea to figure out and ask folks what's going on in that particular tank. So let's take a circular clarifier here, for example. This is a very stripped down and simplified diagram of a circular clarifier. But what we've got here is a tank with a V bottom. It's round. There's baffles in the middle to slow the water down. Water's coming up through the center, and it's flowing by various paths out to the edge and over a weir. And what we've got basically going on is a process to allow small particulates that are in the fluid time to settle out. We've essentially got flow moving from the center to the outside. We've got gravity working for us that's pulling everything in the tank down, and because the solids have a different specific gravity than water, over time, if we give it enough time, they'll sink to somewhere in the bottom of the tank, and then we can mechanically scrape them out so that the water going out of this particular process is clearer and cleaner than the water going into this process. So, there's a flow element here, there's a specific gravity element work at work here. And of course, we can't change gravity, but we can adjust the detention time by changing the flow, basically changing how fast water is moving through this process. And you can use your basic understanding of basic processes like this to sort of, in your mind, calculate how, what answers are likely to be reasonable. Is this a process that's going to happen in minutes or in hours or in days? Get a feeling in your day-to-day work of how long processes typically take, because again, the OPSERT test tests practical knowledge, and you'll be able to use that practical knowledge that you've gained on the job to kind of evaluate test answers and evaluate the answers that you come up with when you're doing the exam questions. Biological processes also need time. You're converting ammonia and nitrates in tanks. Biological processes aren't instantaneous. So having the correct flow rates and detention times is critical. I don't have a diagram of what's going on in here. We'll discuss that in a later session. But same thing goes for something like disinfection. This is a UV disinfection train. Water moves from the left to the right across the screen and is exposed to UV light, which sterilizes any microbes that are left in it before it hits the outfall. And to quote the NMED OPSERT manual, flow velocity must be controlled so that the wastewater is exposed to UV radiation long enough for the desired level of disinfection to occur. So essentially, you're adjusting flow rate or the detention time in this particular train to make sure that the treatment is effective. Let's do a quick refresher on areas and volumes because they're really critical. If you don't have areas and volumes down, it's going to be very difficult to solve flow problems and detention problems because they rely on that. So quick refresher: area, it's how you're measuring essentially surfaces and cross sections. So in a wastewater context, a lot of times that's going to be pipe cross sections or clarifier surface areas or the area of open reservoirs. And in your day-to-day life, it might be how much lawn you have to mow this weekend. Area is always 2 dimensions. There's some units squared. Formulas you should commit to memory. Area of a rectangle or square, length times width. Area of circles, pi r squared. There are other versions. There's one with diameter, but I can never remember that. So it's critical, I think, to have these formulas ready at hand. And it's also critical to have common conversions at hand. Now, you will be given in your exam a sheet like the one I gave you to download that has all of these conversion factors in it. But it's important to have really good facility in moving back and forth between them, because invariable the questions that you get on the exam and the volumes and things you log in your day-to-day job operations are going to be in mixed units, and you need to be able to convert them to the appropriate units so that you can do the math and get the right answer. So again, you can not memorize these and look them up, but if you have some of them memorized, I would focus primarily on the linear conversions, because if you've got those, it makes the area conversions fairly easy. You can very quickly do the calculations you need without spending time looking up whether the formula is correct. So let's start with something really simple. This is going to be our first poll question. If you can throw that up, Kristen. A square foot conversion factor is 144 square inches. So I'll give you 60 seconds, convert 12 square feet into square inches for me. And Kristen, I'm not sure if the poll is up. I can't see it, but if you could just verify.
No, yeah, I'm about to launch it. I just wanted to give people a little bit of time before I launch it.
Okay, good. I was just making sure.
All right, get those answers in. I'm going to close the poll in 3, 2, 1. All right, James, so 77% got the answer right with 1,728 square inches.
Okie doke, perfect. We're on the right track. Just to sort of show my work, this is a pretty simple one. And this is a good way to set these conversions out to make sure that you're converting the right thing. So I've got 12 feet squared times 144 inches squared per foot squared. If I do my math, my units of feet squared cancel out, which leaves me inches squared. So I know I'm in the right place. So 1728 is the correct answer. Let's move on. If you wanted to move back again, it's the same thing. It's a nice thing about conversion factors. You can basically just flip them and do the math. So if I wanted to work my way backwards from square inches to square feet, 1728 square inches times 1 square foot per 144 square inches. You can see I've just flipped my conversion factor upside down. And again, my units all cancel out, inches cancel out, and I'm left with feet. On to volumes, again, quick and dirty review. The nice thing about water is it takes on the shape of whatever container it's in. So, a lot of times you're going to be trying to figure out the volume in a variety of things like tanks or pipes or clarifiers or basins or excavations, or maybe you made salsa this weekend and you want to figure out how much you got. But if you can figure out the shape of the container, you can figure out the shape of the volume. The one thing that you have to be careful of is when you're looking at the depth, you want to make sure that you're looking at the depth of the liquid, not necessarily the depth of the container it's in, because the container could be 10 feet high and you might only have 8 feet of liquid in there. Volume dimensions, always going to be units cubed, square inch or cubic inches, cubic feet, but you might have something in liters or gallons in here, and this is where it kind of gets a little bit confusing. But we get volume by essentially taking our area and adding that third dimension of height or length, which gives us a three-dimensional area, which is a volume. So it's essentially our area formulas with an additional unit attached to it being height or length. Again, you got to make sure that the units are the same so that you come up with the right answer, because they might give you 2 of the dimensions in inches and 1 of the dimensions in feet, or 2 of them in meters and 1 of them in feet. And I can guarantee you the answer you get without doing the conversion is going to be one of the options on the list. So again, conversion factors are key, knowing which ones you're likely to use quite often. And if you're doing practice tests, you'll see which ones show up most frequently, but being able to at least move between cubic feet and gallons and liters, and remembering that a cubic meter is 1,000 liters, not 100 or 10,000, is going to go a long way to helping you do the correct conversions you need to solve these problems, because invariably they give you mixed units to confuse you. So I'm going to leave those conversion factors up. We're going to do another quick question here. Convert cubic meters into gallons. So how many gallons are there in a cubic meter? And all the information you need to do it is in front of you right here. I'll give you a quick hint just to be nice. Those are the things you need to do the math. So give you another 60 seconds or so to run this through. And then Kristen will throw up the answers and we'll see how we did.
All right, get those answers in. I will be closing this poll in 3, 2, 1. All right, James. So we got kind of a mixed bag here. 31% of people said A, 3,785 gallons. 42%, so the highest amount, said B, 264,200 gallons. And then 27% said C, 264 gallons.
All right, so this again is one of those areas where sort of understanding the linear conversions in your head can really come in handy. So here's the math for this. So we've got 1,000 cubic meters. Right here we know that a cubic meter is 1,000 liters. So that's the first part of our equation. So 1,000 liters per cubic meter. But then we've got to convert to gallons. Up here we know that 1 gallon is 3.785 liters. So if we do this correctly, the meters cancel out, meters cubed cancel out, and the liters cancel out, which gives us gallons. So for those who got answer A, your decimal point, you forgot to do one of the conversions. For those who did answer B or got answer C, the decimal point's in the wrong place. But this is also one of those things that if you remember that a meter is about a yard, 1,000 cubic meters is 10 meters, so 30 yards by 30 yards by 30 yards. That's a really big volume. So one way to get to the answer based on what I showed you there as options would be to just kind of eyeball that and realize that that's a really big volume, and you know how big a milk gallon jug is, how many of those are likely to fit in an area that's 10 yards by 10 yards by 10 yards. So again, there's a lot of different ways to skin a cat. Sometimes some of the answers are going to be obviously wrong. Sometimes they're going to be a little bit closer. But if you do your math like this and work your way through the conversion factors, you'll get to the right answer. And again, I think taking the approach of writing things out and making sure that units cancel out will help you ensure that you end up with the right units at the end. All right, so quick and dirty review. Let's move on to the topic of today, which is velocity and flow rates, which introduce a time element. Of course, since most of us learned how to tell time, most of these conversions we have memorized. Everybody knows there's 60 seconds in a minute, 60 minutes in an hour, 24 hours in a day. It may be worth your while to learn some of the longer conversions that, for example, 1 day is 1,444 minutes or 1 year is 8,760 hours. Again, not necessary. You can look this up but it can speed the process up if you have these numbers ready to hand. So this is a rhetorical question. You don't have to answer this, but how many minutes are there in a year? Well, I've got a bunch of different conversion factors here that I can use to get there. So one option would be to go, okay, 365 days times 24 hours a day times 60 minutes per hour gets me to 525,600 minutes. My units cancel out, I'm good to go. But if you know one of the shortcuts, you could, for example, do a shorter equation like 600 or 8,760 hours times 60 minutes per hour. Gets me to the same place, shorter equation, or 365 days times 1,440 minutes per day gets me to the same place. Again, not saying that you have to memorize these, but these are useful things that you could put on flashcards that'll make the test taking a little bit easier. So quick refresher on time, let's talk about velocity. What is velocity? It's speed, essentially. It's the distance or length that something is going to travel in a given amount of time. You're essentially answering a question, how fast is something moving? It's distance divided by time. That distance could be a length, but it's going to be in some units like feet over seconds or feet per second. Good thing to know when you look at these abbreviations, like FPS stands for feet per second. It's essentially a units fraction. Everything in front of the P is on the top. Everything after the P is on the bottom. Of course, sometimes the P is not written in there. Like CFS is cubic feet per second. The per is not written there, but if you sound it out, you can come up with a units fraction and do that cancellation. Could also be, meters per second or something like that. So it's just distance over time. Let's do a quick velocity calculation. I've got the answer options thrown up there. So let's say a duck gets, a small rubber ducky gets sucked into a force main. It's 520 feet long, comes out the end in 142 seconds. So based on that information, you should be able to figure out how fast sewage is flowing through the force main. And you can assume in this case that the duck is moving as fast as the sewage. So let's do this quick calculation. And again, velocity is distance over time.
All right, I'm going to go ahead and launch the poll. Get those answers in. I'm closing the poll in 3, 2, 1. All right, James. So overwhelmingly, 88% said D, 3.7 feet per second, and we're right.
All right, excellent. Yeah. So again, it's distance over time, fractions, distance divided by time. Our distance is in feet. And our time is in seconds. So if they don't tell you to do it in different units, don't change them, use the units you've got. 520 divided by 142 is 3.7. And again, if you look at the answers, 3.7 or 378 is the right answer with the decimal point in the wrong place. So make sure you type things into your calculators correctly. Answer B is obviously wrong. 73,000 feet per second is probably faster than the speed of sound. Look at the answers and kind of evaluate them in practical terms. Like think, could something actually move through a force main that fast? That is an answer that is completely out of the realm of possibility. And if you had time to think about it, and of course on the exam, you're going to have more time than I've given you here to do that, you might be able to discount some of these. So yeah, good job. 3.7 is the right answer. Moving on to flow, it's essentially very similar to velocity. It's the volume that's moving through something in a given time. So you're essentially answering how much, a question about how much volume has gone through a pipe or how much volume has gone through a basin. It's volume divided by time. You're going to see this in units, for example, of something cubed, like feet cubed, over seconds or over minutes or over days. And of course, again, feet cubed might be abbreviated as CFS. You might have gallons per minute as well. You could have gallons per day. You could have millions of gallons per day, or any variation of these. And it's really important when you're looking at these questions to look at the units things are given to you in, and look at the units that the answers are given in, or what it's asking you to figure out, so that you can, again, make sure to do those conversions correctly. Because like I said, a lot of times if you do the math without the conversion, you'll come up with an answer that they've given you, but unfortunately it will be the wrong one. To figure out flow, we basically can do that with two pieces of information. One being the velocity that the liquid is traveling at, and typically we're talking about velocity of liquids here, and the cross section of the fluid or its area, for example, in square feet. And again, sometimes you might have to do conversions, because they might give you an area in feet, but ask for something in a metric conversion. They might give you speed in minutes, but want to know flow in per day. It's a very basic formula like the other one. It's only three variables. Flow equals velocity times the area. Excuse me, divided by area, sorry. Excuse me, times area. So Q equals V times A. So it's velocity times area. Q is a little weird. As a variable, it's actually French. It's the French version of quantity, which, if you think of it that way, it makes sense. The amount of water that's flowing through. So Q is the flow, V is the velocity, and A is the cross section of the flow. So the area of the flow itself, which comes in, as we'll see in a few minutes, into play, because the area of a pressurized pipe is going to be different than the area of a non-pressurized pipe. Or the area of fluid in a pressurized pipe versus non-pressurized pipe. So, and if you look at the units, the math makes sense. Velocity is in, for example, feet per second, area is in feet squared, and those two together, feet squared times feet is feet cubed. So we've got a volume, but the time stays the same. So in pressurized pipes, like drinking water mains and force mains, you can assume that the interior cross-section of the pipe is the same as the cross-section of the water in it. So let's do a sample question trying to figure out the flow in a pipe that's pressurized. I've given you the velocity, which is 2.8 feet per second, and the diameter of the force main, the interior diameter, it's a 12-inch main. So it's 1 foot in diameter. And our flow equation is flow equals velocity times area. So with those two pieces of information, what's the velocity of the sewage flowing through that force main? And again, you're going to have to do a conversion here, because I've given you the diameter in inches and the velocity in feet. So just to give you a hint, you want to convert that diameter from inches into feet before you start doing your velocity equation. Excuse me, your flow equation.
All right, I'm going to launch the poll for this question. And get those answers in. I'll be closing the poll in 3, 2, 1. All right, James. So 59% answered 2.2 CFs. I think that is correct.
That is correct. Yeah, excellent. Good work, everybody. Let's walk through the math on this. Our velocity is given at 2.8 feet per second. And again, I think it's always a good idea to write out those units as fractions so that you can cancel them out. The trick to this one is that you've got to calculate the area or the cross-sectional area of the fluid, which is essentially the cross-sectional area of the pipe. And to do this and get everything into consistent units, you have to turn 12 inches into feet. 12 inches is 1 foot. Our cross-sectional area for a circle is pi r squared. There's also a diameter version, but I'm using the pi r squared version here. So our area formula is pi times half of a foot squared. So 0.5 squared times pi. That works out to 0.785 square feet. That's our area. So if you got something other than 2.2, this is probably where you went wrong. And then if we multiply this out again, we've got 2.8 feet squared times 0.785, 2.8 feet per second times 7.785 feet squared. Our units of feet and feet squared multiplied give us feet cubed. 2.8 times 0.78 is 2.2, and our seconds stay the same. There's no change. Those don't cancel out. So we end up with a volume, feet cubed or cubic feet per second. That's the math. Look at what you did, compare it to that equation. Again, make sure decimal points are in the right places and make sure that you square the right thing. So you don't want to multiply pi times r and then square the result. Remember the PEMDAS rules that Rose talked about last time, the order of operations. You would do an exponent before you do multiplication. So make sure you write that out. So our answer, our correct answer, again, 2.2, most of you got that right, which is great. So that's in a pressurized pipe, which you might have coming out of a tank or, like I said, a force main. Unpressurized pipes, like most gravity sewers, culverts like this, I put a picture of a culvert instead of a sewer because it's prettier, are not designed to typically run full. So when you're talking about flow rate in a sewer, first make sure you know whether you're talking about a force main or a gravity main so you can determine whether you can use the cross-sectional area of the pipe or whether you have to take it to another step. If it's unpressurized, you need the cross-sectional area of the effluent in the pipe, not the pipe itself. So I'm going to give you a similar equation to the one that we did before, but this is going to be looking at velocity because you need to get comfortable with the formula, and be able to work it backwards and forwards because it's got 3 variables, Q, V, and A. If you know 2 of them, you can figure out the third. So here's a question for you. You are trying to verify that your 12-inch or 1 foot gravity mains are maintaining a minimum scouring velocity of 2 feet per second at peak flows. Inspection shows that at peak flow, they're half full, and the flow has been calculated for you at 300 gallons per minute. So what you want to know is, A, what is the velocity? And then secondarily, based on the velocity you calculated, does that meet your 2.0 feet per second scouring velocity goal? So remember, in this case, it's an unpressurized pipe. As I've shown in my little diagram over there, it's running half full. So the key to this is going to be turning feet into inches, or excuse me, inches into feet, and making sure that when you're doing your area calculation, you're not calculating the area of the whole pipe, you're calculating the area of half of the pipe because that's where the water line is. It's halfway up. You also are going to have to convert gallons per minute into feet per second, or into gallons per second. So there's a couple of conversions that you have to do here. I've given you a few answers as options. And so see if you can work this out. The steps that you're going to want to take is figure out the area, convert the flow, and then use those to calculate the velocity. So, and just so you know, your formula Q equals VA, what you're looking for is V. So you can do that by dividing both sides of the equation by A. So you end up with flow divided by area is going to give you the volume. We'll give you a little bit longer on this one too. And just to harken back to our earlier session on test taking tips, you can see I've drawn out a little diagram here on the right hand side of what I'm looking at, which reminds me of the area that I'm looking for. Again, the visual approach doesn't work for everybody, but if it does work for you, drawing little sketches like this of what you know about the problem can be really, really useful in helping make sure that you do all of the steps. All right, let's get our answers in and see how we did.
All right, get those answers in. I'll be closing the poll in just a couple of seconds. All right, James, so 54% chose 1.7 feet per second.
Excellent, that is the correct answer. I'll walk through the steps here as well in just a second. But again, evaluate the answers, sort of use practical knowledge. And again, this is where I think like linear conversions can really come in handy. 700 something feet per second. Think about how fast that actually is. That would be that the sewage is moving through there at about 250 yards per second, which would be an astronomical speed. So you could probably discount D offhand. The other ones are all fairly close. A, you might get if you did the math, but again, maybe messed up the rounding or put the decimal point in the wrong place. So let's walk through this. As I said, the key here is that the pipe is only half full, and what you're looking for is the area of the cross-sectional area of the fluid, not the actual pipe. So you're going to find the area of the pipe and divide it by 2. So we work that out. We actually end up with an area of 0.393 or 0.39 feet squared. So now we've got our area. They've given us the flow Q, but it's in gallons per minute, and we have to get it into units of cubic feet per second so that the math works easily. So our next step is going to be changing that from gallons per minute to cubic feet per second. So we can do that using our conversion factors. So 300 gallons per minute, if we're doing it stepwise. We know that there's 60 seconds in a minute, so 1 minute over 60 seconds, multiply that straight across, and you get 5 gallons per second. So now we've got one of our units correct, seconds. Now we just got to turn the gallons into cubic feet. Our conversion factor for that, and we can double check that our units cross out, our conversion factor for turning gallons into feet is 7.48. So again, simple equation, 0.5 gallons per second times 1 cubic foot per 7.48 gallons gives me 0.67 cubic feet per second. Now all of my variables are in the same units, so I can do this pretty straightforward. Again, checking my units. So now I set up my equation and solve for velocity. So I know Q equals VA, which means V equals Q divided by A. So if I set up the equation with sort of in the standard Q equals VA format there, I know I can essentially move the 0.393 to the other side and divide 0.76 by that to get the velocity, which then gives me 1.7 feet per second. And I can check that my units are right because I've got feet cubed over feet squared. So the 2 cancels out 2 of the 3, which leaves me feet to the 1 power, which is just feet. So I asked you a 2-part question. The first part is 1.7 feet is the answer. So if our goal here was to maintain 2 feet per second scouring velocity, the answer to the second part of the question would be no, it's actually not enough velocity. Then of course we'd have to, in real terms, in real life, maybe figure out what's going on and why that is, maybe go back and double check our math because we would expect the pipe distribution network to have been built correctly, but things don't always work out the way we're supposed to. So again, this is a flow question, but you're just solving for one of the other components. Using flow to get volume. Sometimes you have to use flow and volume to get area. Sometimes you're going to use area and volume to get flow. So again, facility with working these back and forth is really key. Like I said, not enough velocity. So when you're looking at these equations, it's a good idea. I sometimes, when I'm taking math tests, will write out equations and their different forms at the top that I know I'm going to use. So again, Q equals VA, so A equals Q over V, and V equals Q over A. You just have to figure out which one you're solving for. And again, so flow is velocity is flow over area. You can cross out the units, and you end up with the right units. Again, as I've said before, conversion factors are key. Some of these are probably worth memorizing just so that you don't have to look them up. Assuming you've got a cheat sheet in front of you, and if you don't, 1 cubic foot is 7.48 gallons. You can just write that down, but you've got other versions here as well. Let's try and convert 1 cubic foot per second, so 1 CFS, into millions of gallons per day. How would you do that? So the key to this is going to be being able to convert cubic feet into gallons, seconds into days, and then of course, not forgetting to factor that the answer is in millions of gallons per day, not gallons.
All right, get those answers in. I will be closing the poll in 3, 2, 1. All right, James, so overwhelmingly 65% said 0.65 millions of gallons per day, which is the correct answer.
That is the right answer. And several of the other answers are going to be options that you would get if you forgot to do the conversion. So for example, if you put down 8 million gallons per day answer, you probably forgot to convert minutes into seconds and got the gallon to cubic feet conversion backwards. If you got answer number 3, you probably forgot to convert the gallons answer into millions of gallons. So let's walk through this. Stepwise, adding all of this into a single equation. We know a cubic foot, we got a cubic foot per second. We need to turn that second into days. So I'm going to do the time conversion first. So I know there's 60 seconds in a minute and 1,440 minutes in a day. So this part of the equation here takes care of my time conversion of seconds into days. And then I know that a cubic foot is 7.481, excuse me, I've got that backwards. 7.481 cubic feet is gallons per cubic foot. And assuming I did my math right, should come out to 0.685 gallons per day. I think I actually did my math wrong there. But yeah, the correct answer is 0.685. I apologize for that. Another thing that you might want to brush up on is calculating averages, because quite often you're going to have things like flows given in average daily flows, and they'll want something over the course of a year or vice versa. This is not a question that you have to answer, but if we were given something like this, we've got a month of monthly total flow volumes and an annual total. If we were trying to figure out the average daily flow of something like this, we'd have to take the total flow for the period and divide it by the total number of days. Again, have to do some conversions here. That's to add up our flow, which fortunately has been done for us already here, 600. And then we have to remember there's 365 days in a year. So if we work that out, we end up with 1.64 mgd. Just sort of an aside, something that you're going to probably need to look at some point. All right, last but not least, let's look at detention time. We've got about 10 minutes left, and that should be enough time to look at this. It's a basic concept. Again, it plays an important role in a variety of contexts: primary sedimentation, digestion, aerobic digestion, anaerobic digestion, flocculation, mixing, etc. So just to remind ourselves, detention time is the amount of time that water or effluent stays in a given reservoir or treatment process, right? So it's the volume of the basin that we're talking about divided by the flow through the basin. And this is where I think it's a really good idea, again, to be able to visualize what's going on. So this is a cross section of a sedimentation basin, a rectangular primary sedimentation basin. We've got fluid coming in from the left, going through a baffle, which is slowing it down, and slowly making its way over to a weir on the right-hand side, where hopefully some cleaner water is going out. So what's going on in here? We've got flow direction from left to right. We've got solids in there, which are represented by this little cloud here. Obviously, they're a lot smaller than that in real life. And again, we've got gravity working in our favor. So if we slow the flow down enough, the fact that there is a differential between the specific gravity of the small particulates in the water and the water itself means that over time, those will sink to the bottom and we can scrape them out, and cleaner water is going to go out than it went in. So, let's talk about what's going on sort of in this process. Talking about primary sedimentation, what's going on in a primary sedimentation process? Well, the purpose is removing readily settleable solids, reducing the suspended solids content in the effluent. So how's that happening? Again, velocity is being slowed down as it moves through the tank. Small particles have time to sink, clump together. You might use flocculants to speed that process up. The end goal is that the effluent that flows out of the weir at the end is cleaner than the water that came in because the solids have sunk to the bottom and are being moved mechanically. So that's what's going on. You know, what's the likely impact? Well, it kind of depends on the efficiency of your system and how well it's built. But you know, one of the main goals here is removing BOD and TSS, total suspended solids, biological oxygen demand. If you look at some reference guides, you could potentially move up to about 70% of TSS and maybe up to 40% of BOD in an efficient system. Obviously, every system is going to be a little bit different, but the removal is a function of both the concentration coming in and the detention time. So it takes time. Those fine solids need time to coalesce, flocculate, and sink. Typical ranges for a rectangular tank like this might be in the 1.5 to 2.5 hour ranges. Might be shorter, they might be longer, depending on what your system actually needs and the level that you're trying to treat them to. So knowing kind of what's going on in the process, again, can help you figure out how to answer the question, because you can sort of visualize in your head what's going on. So let's calculate a detention time. Relatively simple. Again, detention time is volume over flow. Volume divided by flow. The units have to match. In this case, we've got a sedimentation basin that has 2 clarifiers and an average flow rate of, that should say flow rate, of 20,000 cubic meters per day. Everything is in meters here, so you won't have to do those kinds of conversions, but you are going to have to figure out volume. So each of the 2 clarifiers, we've got length of 42, a width of 6, and a height of 5 meters, but the side water depth is 4 meters. So you're going to need to find the volume of this, and then you're going to have to figure out the detention time in hours. Remember, you've been given the flow in days. So there's a couple of conversions you have to do here. We'll give you about 2 minutes to do this. And then we'll give you a brief intro into some of the topics we'll discuss in later sessions, and I'll let you know about some resources. And just know that that 2 is highlighted for a reason. So I've made it a little simpler. I've given you 2 answers, or 3 answers instead of 4 this time. So our options are a little over 1,000 hours, 1.2 hours, or 2.24 hours.
All right, get those answers in. I'll be closing the poll in just a couple of seconds. All right, James, so 66% were correct with 2.24 hours.
Excellent work, everybody. If you got answer number 1, you probably forgot to convert from days to hours. There was one step that you left out. If you got answer 2, 1.21 hours, you only calculated the volume of 1 basin. This is, again, just to sort of point out that you really need to read the questions closely. It's 1 basin, but it's got 2 clarifiers. So what you were going to have to do is calculate the area of 2 of these for your volume, not just 1. So a little tricky here, but everybody got most of it right, and some of you got all of it right. So again, the volume here, we're looking for the volume of the fluid, not the tank. So our depth dimension is 4 meters, not 5. So it's 42 times 6 times 4 times 2, because we've got two clarifiers in this particular basin. So our volume is 2,016 meters cubed. Now we have to calculate the detention time. There's a couple of ways you could do that. So our detention time is going to be the volume, 2016, divided by the flow, which is 20,000 cubic meters per day. So one of the possible answers is 0.1008 days, but that's the wrong units for the question, because it asked you for this in hours. So you have to do one more conversion here. So we know that there's 24 hours in a day. So if we multiply that 0.1008 days times 24 hours in a day, the days cancel out and we get our 2.24 hours. And again, checking our units to make sure we got where we want to be. Always a good idea, again, once you've done the math and got the answer, to double check the question just to make sure that you answered the right thing. Because I know I've done that many times where I've gotten like 9 steps through a 10-step question and thought I was finished. Excellent. So that's a quick and dirty run through the basics of area, volume, flow, and detention time. You're going to use these in a lot of different contexts, primarily or often dealing with things like removal rates. So those are obviously going to be a topic for a different training, because you sort of have to have the building blocks to calculate the flow and the detention time before you get on to figuring out what's going on. But again, the processes are happening. Solids are settling out in your primary detention tank. At some point, you're probably going to be asked questions about how efficiently are they being removed, or you're going to need to know that in your day-to-day work, because things change over time. Temperature affects things, the flow will affect things. So this is just a brief example. If you were going to try to figure out the primary sedimentation removal in a rectangular basin, there's a formula for that. If you need it on a test, it'll be given to you. And in this case, the formula is R equals T over A plus B times T. A and B are actually empirical constants. Again, if you needed to do this on the test, you would be given them, but you could figure out, like if I'm trying to figure out what's the expected removal efficiency for BOD in a tank with detention time of 2.42 hours, I'd use my constants to do this math here, and I could expect that at least at reasonable temperatures, I'd have around a 36% BOD removal rate. This equation happens to work for both BOD and TSS. Happen to have to use different coefficients. But if I was going to answer the secondary question, what's my TSS removal rate, I could do the same formula with different coefficients and come up with an answer of 58%, which is kind of a good point to understand that sometimes a single process is doing multiple things, but it's not necessarily doing them at the same rate. So if you got a question, for example, that said, give us, the BOD and the TSS removal rates, and you just did the one calculation and applied that to both, you'd end up wrong on the second answer, because in this case, same detention time, but very different removal rates. The TSS removal rate's almost twice what the BOD removal rates is. And again, we'll get into this more in later sessions, but it's good to recognize that these processes, these mechanical processes, these physical processes, these biological processes can be affected by a lot of different things, temperature being a key one. So this is primary sedimentation performance at about 70 degrees is much higher than it is at close to freezing. This graph reads kind of backwards, but if you were going to try and figure out what your settling time was at 35 degrees, you do that equation and then multiply it times 1.75. So at freezing, this process takes almost twice as long as it does at 75 degrees. So again, just a preview of coming attractions. I realize we're a couple of minutes over, and I apologize for that, but we will open the floor for questions if anybody has any. I do want to point out website, swefc.unm.edu. This is also in the handout that we've been given. And I do want to do a plug for technical assistance. We've mentioned many times that the funding for these training sessions also has a technical assistance component to it. We're essentially consultants that work for you for free. We are your tax dollars at work. One of the things that we're doing under this particular grant is pre-treatment technical assistance. So if your system needs help, maybe implementing a domestic or commercial fog prevention program, or dealing with EPA dental rule compliance, or developing any other aspects of a pre-treatment program, please reach out to us. You can do that on the website at efcnetwork.org, where you signed up for this webinar and the others in the series, or you could just email us directly. AJ, I believe, is heading up that kind of that particular project. But if this is something you're interested in talking about or getting set up, please reach out. Again, we're there for free. All it costs you is a phone call, and I don't think those even cost a dime anymore. So with that, we'll open the floor if there are any other questions, and I will throw up our contact information just in case you want to get in touch with any of us, and we'll go from there.
All right, and while we wait to see if there's any questions coming in, I'd like to thank you, James, for sharing your expertise with us today. Just so everyone knows, following this webinar, you will receive a follow-up email with the slides from today and a link to the recording. We ask that you complete the webinar evaluation following the webinar so you can let us know your thoughts on today's session, as this helps us plan future webinars on topics important to you. Thanks again. We hope to see you at future EFCN events. And I'm not seeing any questions, so I will go ahead and close out. Thank you, James.
All right, thanks. We'll see you next time.